All right, so I will start the webinar here. Actually, do you guys see my full screen?
I see the slides, and now I see your slides and the next slide and your notes.
Okay, you do see the notes.
Yes, correct.
How about now?
I only see your slide.
Okay, perfect. So, all right, so we'll get started here in 3, 2, 1. All right. Welcome, everyone. Thank you for joining us today for Unlocking CDR's Potential. My name is Alex Krauka, and I am a consultant with the U.S. Energy Association's Consensus Program. For those of you who may not be familiar with the Consensus Program, it is a cooperative agreement that we have with the U.S. Department of Energy's Office of Fossil Energy and Carbon Management that seeks to educate the public, policymakers, industry, and other stakeholders to build a consensus on the benefits of and requirements for CCUS and other carbon management technologies, such as carbon dioxide removal, which we'll be discussing today. We do this through a variety of methods and activities, such as hosting briefings and webinars. We have workshops, both in-person, virtual, as well as hybrid. We work with some of our subcontractors to put out various white papers and reports, one of which we'll be discussing today. And then we also have monthly news clips that we put out to help keep our stakeholders informed. If you'd like to subscribe to our mailing list, please email my colleague Michelle Littlefield at mlittlefield@usea.org. A quick note on logistics for today. We are recording this webinar and plan to post the recording as well as copies of the presentations on our event page. Just please give us a couple of days for that to be completed. Q&A will be held after each presentation. And we ask that you use the Q&A box at the bottom of the Zoom window for questions and comments. So what brings us here today? This is kind of a cool visual that I like that kind of shows the problem that we're dealing with in the amount of fossil fuels that are being produced globally. We need to deal with the emissions from the production of these fossil fuels, and as you can see, it's a tremendous amount. What does that mean? In the context of carbon removal, we need to remove 10 billion tons of CO2 annually by 2050. That's the number that's been cited by the IPCC. So it's going to take a lot. It's a nascent industry at the moment. However, moving rapidly, developing very quickly, and you're seeing headlines about it every day. But that's also what brings us here today is really how can we unlock CDR's potential here. So we're lucky to have 3 great speakers join us today. We have Jason Grillo, Director of Partnerships and Operations at AirMiners, Dr. Dave Luebke, Technical Director at the National Energy Technology Laboratories Direct Air Capture Center, and then Joel Smichak, Senior Research Scientist at Battelle. Their bios are on our event page, so feel free to check them out. In the interest of time, I'm not going to go over them because I want to get straight into the nitty gritty. So with that, I'm going to pass it over to Jason to go ahead and discuss the awesome work that AirMiners is doing and how they are supporting entrepreneurs in the CDR space. With that, Jason, the floor is yours.
Great. Thanks, Alex. It's a pleasure to be here today. So I'm going to share my screen and talk about AirMiners, which is the organization that I work with. Again, thank you to you all as an audience. Looking forward to sharing a little bit about what I do, what AirMiners does, and how we look forward to working with you all in the future. So AirMiners is an organization that is virtual, but I wanted to back up and think back to some of Alex's points earlier. Why are we having this meeting? What is the purpose of our gathering today? And in AirMiners, our answer to that is that we need to remove carbon from the atmosphere, right? It wouldn't be a climate tech presentation without some version of this chart, which is modified from the IPCC. Again, this is a representation and somewhat stylized, knowing that on the business as usual path, this is what the amount of emissions are looking to increase. If we want to get to 1.5 degrees C by mid-century, we need to not just be carbon neutral, but carbon negative. And that's where carbon removal comes into play. AirMiners' mission, in fact, is to be removing that first 1 billion tons of greenhouse gas from the atmosphere by the end of 2030. Mostly carbon dioxide, but we say CO2e here to leave room for people in our community who are methane or nitrous oxide focused. But that's the mission. And our primary activities in AirMiners fall out from that mission. First, our boot up, which I'll talk about in a minute, and then our community of over 2,300 people worldwide, our Launchpad Accelerator program, and also our Kiloton Fund, which we recently launched. So what we do in AirMiners, for one thing, we provide an entry point for those who are brand new to carbon removal, who want to develop their interest, who might have read about carbon removal in an article or heard about it on a podcast and want to get into what the industry is. This is a convenient starting point for in-depth knowledge of CDR in a virtual learning session in groups over the course of 5 weeks. It's a sprint. And to sign up for that for free, it is bootup.airminers.org for those who want to learn in conjunction with others about the broad overview of carbon removal itself. Our AirMiners, that leads directly to our AirMiners community. The boot up is separate, and then you can join our main AirMiners community. AirMiners has been around since 2016, and our community has grown to over 2,300 innovators worldwide. When I say innovators, I mean engineers and scientists and designers and entrepreneurs and a venture capitalist or two or three, policy experts as well, who are in our community and are advancing carbon removal solutions worldwide across any method of carbon removal. And that includes oceans and forests and soils and mineralization and biochar, and yes, indeed, direct air capture, which we'll talk about in a minute. It's a self-sustaining community. Collaboration and support is a hallmark of what we offer for others to be able to bounce ideas off of everybody else, because as Alex mentioned, this is a still very, very early stage industry. You know, the landscape of carbon removal is very much a landscape of startups. While there are a couple of dozen companies that are starting to punch through and get, Series A funding and offer carbon removal credits on the tens of thousands of tons level, I can say from my experience that we've had 700 or 800 teams apply to our Launchpad program at the 2 and 3 and 4 person stage, and I'll talk about Launchpad in a slide or two. But the community is the heartbeat of what we do in AirMiners, because it offers a space for people to talk about what they're working on, share ideas, vet them, and improve. Launchpad is our accelerator program, and we've run that since the summer of 2021. Every quarter or so 4 batches per year, we have worked with startups of, like I said, 2 and 3 and 4 people across any method to hone their story, to instruct them on best practices of negotiations and how to work with investors, how to pitch your company, understanding what carbon markets are all about, or to impart a greater understanding of techno-economic assessment. Those types of learnings we find are critical. Also, there are groups of 10 to 15 teams in each batch. So as much as the batch members can learn from us, they can also learn from their fellow batch mates. To date, we've graduated 95 teams, and among our alumni, they've raised over $90 million in grant and private investment funding. The next batch is going to be have its applications closing on October 13th. So airminers.org/accelerate is the link to look at. And Alex, feel free to share these slides later, which will have the hyperlinks in them as well. Like I said, it's been my pleasure to work with nearly 100 teams over the course of the last 2 years, along with other members of our own internal AirMiners team to make that happen. Many CDR startups are approaching the quintessential valley of death. That's through their dealings. That means, for one thing, they're looking for cash flow from sales to cross the quintessential chasm in Jeffrey Moore terms, so to speak, and also see that valley of death where entrepreneurial and seed angel investors can only provide so much before venture capital comes in. And to bridge that funding gap, we started something that I wanted to talk about next, which is our kiloton fund, to help assist carbon removal startups with a small amount of funding in exchange for carbon credits to be delivered in future years. This establishes the early success of the pilot kiloton fund. We are also planning on potentially starting a megaton fund. The kiloton fund is a test vehicle for figuring out how the megaton fund might work. The idea behind all of these options is to provide immediate revenue for startups fueling their operations, and later in exchange for carbon removal credits in the future. Finally, I would note that we are also building out a Pioneer DAC program for those interested in direct air capture, actively constructing this program tailored to the needs of direct air capture startups. I would note that AirMiners itself is an EPIC DAC Phase 1 winner from the DOE that was announced maybe 2 weeks ago. And they were also aimed to submit for Phase 2 of that program. Think it, design it, build it. We were a winner from the Think It phase. We're moving on to the Design It phase. We seek to partner with National Energy Technology Labs for direct air capture testing sites. And we have had among the 95 alumni, about 1 out of 5 are direct air capture teams. Additional CDR methods, I should note, are on the radar for future partnerships with NETL and others at DOE. Oceans in particular comes to mind. I happen to be located in the state of Washington, and noting that the PNNL at SQUIM is a site that recently announced that they're working with Ebb Carbon, which is an ocean carbon removal team. So not an alumni team, not the Launchpad team, but still they're a carbon removal team. And across all methods of carbon removal, we're interested. That said, the DAC Pioneer program is where we're going to be emphasizing in the here and now as we go forward. And this is my last slide. We're accelerating the removal of 1 billion tons of carbon dioxide by 2030. That's our mission. It's our pleasure to work with USEA. It will be our pleasure. It's our pleasure to work with. Will be our pleasure to work with NETL and other stakeholders in the future. And I just want to say thank you so much for your time. My contact information is at the bottom, and I'm happy to entertain any questions that you may have of me and AirMiners.
Great. Thank you so much, Jason. Really exciting stuff that you guys are doing at AirMiners. And I think that's exactly the type of support that the entrepreneurial community is seeking and needs. Just to let everyone know, Jason's only going to be with us here for another about 15 minutes or so. He's got another engagement that he needs to attend to. So if anyone has any questions or comments for Jason, now would be the time. Looks like we have a raised hand. Can ideas from abroad be included?
Absolutely. In Launchpad, yes. More than willing to have people included in the Launchpad. A significant fraction of our Launchpad teams are ex-US.
That's awesome, and I know I've noticed that in the AirMiners Slack is there's a lot of engagement internationally.
Yeah, I would note that about 2/3 of our community, because I manage the community among other things, but 2/3 of the AirMiners community is North American, US, Canada. We were in, maybe a quarter of which are in Europe, including the UK, and a good number of teams are, and a good number of people in our community are from Latin America, Sub-Saharan Africa, Middle East, India, Southeast Asia, Australia, New Zealand. In Launchpad, we even graduated our first Australian and New Zealander teams a couple of months ago. Our sessions are at 9 a.m. Pacific, so you can do the math about the ungodly early hour of the morning that those teams had to wake up in order to participate, but they did. And again, happy to field and work with teams worldwide.
Awesome. And then contacting Launchpad, should they just contact you directly, or was there a separate contact there?
So our team is 3 people. It's myself, Tidor Jankowski, and Adina Mangubat, who's our accelerator director. I would say that you can email launchpad@airminers.org, and I can share that in the chat here. For the audience. Oh, I can only do hosts and panelists. But Alex, if you could, launchpad@airminers.org.
Yep, I will type that in just a moment here.
Or you can try my own personal email at AirMiners, jason@airminers.org.
Just type it in, launchpad@airminers.org, correct?
Yes.
There we go. And then your website says the Kiloton Fund is closed. When will it restart?
Sure. So the application is closed about a week ago. So that's finished. I would say look to the Megaton. Look, again, we do not have a timeline for the Megaton Fund. I can't really talk too much about it right now, but that would probably be the next opportunity. We're not going to reopen the Kiloton Fund. Our plans right now are to just do diligence on the applicants whom we've received for the Kiloton Fund, with decisions due later this year.
Awesome. And then can you discuss if you have any interest in collaborating with US universities?
So we are willing to entertain partnerships with universities. We have quite a few relationships with various universities around the world. A Global CO2 Initiative at the University of Michigan is probably the closest we have, and we've worked with them on doing techno-economic assessment for what our teams do. I would say open to any and all university collaborations in the future. What AirMiners does really well is to get those ideas moving forward at that founding stage. That if you're speaking to you, if you're sitting on IP at a university lab that you want to bring into a field environment to start a company and spin that out of your university, great. If you're at a national energy technology lab and you want to spin that out into a company, then more than happy to bring you into the AirMiners community. You can work with other people to help make that happen.
Awesome. And then can you talk more about what types of CDR technologies you're funding and how that kind of, I guess, coordinates with the breakthrough and EIP efforts and funding?
So when you say technologies that we're funding, to be clear, Launchpad does not do equity funding for their teams. It's a free service. We don't take equity. We don't take money from our teams, nor do we give away money in the Launchpad program per se. Launchpad is, also to be very clear, standalone from the Kiloton Fund. So, and we have not yet, and the Kiloton Fund is going to be a portfolio of a variety of approaches and methods of carbon removal represented.
Got it. Thank you. And then what is the extent of the funding based on technology TRL. I guess I interpret that as asking kind of, on average, what TRL levels are you guys, is AirMiners kind of working with?
Sure. For Launchpad, again, there's no, I mean, we will take companies at an early TRL. We like to see that you are out of the lab and into, if not field testing, then deployment, then deployment. We really like to see that you're free and clear of a tech transfer office. We feel like we have the best resources to offer teams who are in that state, and who are at that point in their development. Also, to be fair to you as teams, because we want to be able to advise you as a company based on your ability to pivot and move with advice that we offer. What we don't want to have happen is someone to get into our program and say, well, I can't do this. I have to figure out like whether or not I'm even allowed to do something based on who owns the intellectual property. I would advise that once you're free and clear of that situation, that's the best time. That's the best time to apply. We take teams who are more or less at the pre-seed stage of development. They might have angel investment, they might have grant funding, but they have the ability to develop their own intellectual property as they see fit in the world.
Got it. And then kind of a follow-up question to that, what is the average size of your investment? I might adjust that a little bit to be kind of, what's the average valuation of companies that have worked with AirMiners?
Sure. So I can only talk about Kiloton Fund right now. What the plan is for the Kiloton Fund right now. The Kiloton Fund is a $250,000 fund. It is not a large fund by fund standards. That said, it is a test vehicle for a larger megaton fund to come later. We have announced that the idea is to fund companies with $10,000 out of that Kiloton Fund money, 20 teams, with that $10,000 each in exchange for carbon removal credits in the future.
Got it. And then one last question, and then I think we'll let you off the hot seat here. Is any chance for scale-up partnership for the DOE DAC project? So I'm wondering if that's kind of referring to the DAC hubs. And I believe you guys were awarded one of those or one of the teams, or am I incorrect in that?
So we're not participating as a named company in the DAC program, in the DAC hub program that was just announced maybe a month or so ago. AirMiners is not part of any of the 19 or 20 different hubs at various at various tiers of development. So we are not part of that. What we did announce 2 weeks ago is that we are prize winners from the DOE's Epic DAC prize competition. So that is a different program from the direct air capture hubs. To be clear, that is considered wholly and separately different from the DAC hubs that are funded by the bipartisan infrastructure law.
Yeah, that's my mistake for confusing those. Do you want to just talk to that that prize or that award that you guys did receive?
So sure. So the Epic DAC prize, sure.
Yeah.
Again, it's for accelerator programs to bring direct air capture ideas to light. Again, to be clear, direct air capture is one of many different methods of carbon removal that we gladly support, and it is, that said, a very important aspect of what we are. Of the teams we were working with, a very significant fraction of the various methods, and we are happy to be happy to be working with a number of alumni teams. Direct Air Captures is a vibrant community within the carbon removal community. There's even a whole separate DAC coalition for direct air capture policy efforts that is not part of AirMiners, to be clear. But again, we're happy to work with them on various projects. They've come onto our event series from time to time as well as presenters and speakers. So yes, so I'm happy to entertain collaborations in the future for the EPIC DAC phase 2 and ultimately even perhaps phase 3 of that effort that the Department of Energy is offering. So again, jason@airminers.org is my own personal email at AirMiners. So feel free to email that. And Alex, if you could share that as well in the chat, that might be helpful for people, I'm hoping. Thank you.
Love it. Well, Jason, I know you need to get going here in a few moments. So just want to say thank you so much for joining us, sharing the awesome work that you guys are doing at AirMiners. Clearly a lot of interest just based on all the questions and comments that were coming in. So hopefully this was valuable for you to join us today, and some great work comes out of it afterwards.
Thank you, Alex. And just to underscore, it's a team effort, and I really couldn't do this without the help of my fellow principal collaborators in AirMiners, who are Teeter Jankowski, our CEO, and Adina Mangabat, our accelerator director. So, thanks to them and to the efforts of all the other AirMiners in our community. That's how we're able to achieve what we can. So, and look forward to inviting more people into that community in the future as well.
Yeah, well, most definitely. Excited to see you guys scale. All right. Well, next up, we have Joel Smichak from Battelle to discuss a study that USEA and Battelle collaborated on, looking at life cycle analyses of various CDR methods. So, if you're an aspiring entrepreneur and you're trying to decide which path you'd like to go down, I think it's certainly important to kind of look at life cycle assessments of the methodologies that you're considering. So luckily, we've had Joel and his team at Battelle take a look at this over the last year or so. And he's here to kind of present some of their findings and considerations for everyone involved. So with that, Joel, I'll pass it on to you.
Okay, thank you, Alex, and thanks everybody for joining this webinar. So I am Joel Smichak. I'm a research scientist at Battelle. Battelle is a nonprofit research institute. We're headquartered in Columbus, Ohio. Been around since the 1920s, so close to 100 years. My co-authors include Devin Dixon, Brandon Webster, and a lot of other people have kind of contributed to this study. So I'll be talking about CDR technologies like direct air capture, mineralization, reforestation, bioenergy with carbon capture and storage, and how they may generate some greenhouse gas emissions in their operations, and how that needs to be accounted for when looking at the performance of these CDR technologies. So that thanks to USEA for supporting us on this project. We think it's kind of an important topic to consider when you're looking at CDR technologies. So I won't dwell on this disclaimer. It's pretty standard. So our objective of this study was to review the status of carbon dioxide removal technologies, and we did this work, circa winter 2023. There's been a lot of advancements in development of these technologies even since then, and we wanted to compare kind of the real world operations for these CDR technologies at scale and see what's their net CO2 removed. And then finally, develop recommendations to kind of optimize CDR development in the US to maximize the net CO2 removed. So the concept is, you have, these technologies remove CO2 from the atmosphere. but they also may generate some emissions based on their, their capture operations, the CO2 storage, land use changes, biomass harvesting, things like that. So the difference between those is the net CO2 removed. When we did our study, there are over 50 CDR technologies, probably more currently. And yeah, it's an area of active technology development. So to constrain our scope, we focused on 5 technologies: low and high temperature direct air capture, bioenergy with carbon capture and storage, or BECCS, reforestation, and mineralization. So these technologies at that time seemed to have the most near-term potential for widespread application at scale. So as far as our methods, our first step was to review these CDR technologies, how they work, how much equipment, materials are necessary, what's the overall process. We did a literature review of other LCAs for CDR technologies. And then we analyzed our 5 technologies with a kind of a baseline scenario of 1 million tons per year with a kind of a streamlined energy and emissions life cycle model. We also evaluated geographic market factors for CDR development in the US, and finally came up with some recommendations for options for CDR development in the US, again, to optimize the net CO2 removed. So like all life cycle assessments, there's some assumptions and limitations involved with this study. We did our best to do a cradle to grave life cycle assessment. We use this kind of streamlined energy emissions model with the objective of comparing the net negative emissions for the different CDR technologies. So here on the right is kind of an example of a direct air capture system where you have energy that powers the direct air capture plant, and then you have to compress and transport the CO2 to a CO2 storage site and inject it underground these deep geologic reservoirs. So all those items might generate their own greenhouse gas emissions in some way. So those need to be accounted for when you're trying to come up with this like net negative assessment. So again, these technologies, they're in the early stages of deployment. We do think you need, like some structured testing, long-term operational monitoring of the systems. It might be for 5 to 10 plus years to understand practical aspects of their operations, natural cycles, energy sources, all those effects on their greenhouse gas emissions. One thing is in our literature research, there's a lot of studies out there on CDR life cycle assessments, but a lot of these studies kind of focus on just one aspect of the overall cradle to grave system. Like it might just be like the actual like direct air capture plant rather than the full, like where's the energy coming from and the CO2 storage and things like that. So that's important to consider. So when we did this status review of CDR technologies in circa winter 2023, we saw that there's over 200 CDR projects at various scales around the world. A lot of reforestation projects, a lot of research on direct air capture. A lot of different technologies out there. Again, we kind of had to constrain our scope to these 5 technologies that we focused on. And we were reviewing these technologies in terms of, what's the overall process, what's the deployment scale, costs, and what's the technology readiness level. So I'll do a quick review for these 5 different CDR technologies we looked at. So bioenergy with carbon capture and storage, or BECCS, is a technology where they can harvest and burn biomass to generate electricity, and then they capture the emissions from the plant and store it underground in these deep geologic reservoirs. So these systems, they're big facilities, they're big plants. There's a lot of construction. There's a lot of transportation of your biomass. There's land use with the biomass. A lot of these BECCS plants, we noticed that they were planning to use fuel mixing, so they weren't going to burn just biomass because it was difficult to get a reliable supply of the the biomass that they need. So a lot of them are considering, burning fossil fuels in addition to the biomass. Then the whole biomass production, transportation, energy production. Those are a big contributors to the greenhouse gas emissions for BECCS. For direct air capture, we looked at, again, low and high temperature direct air capture. And again, these facilities would, have to process large volumes of air. They're going to need a lot of energy to run that direct air capture system. There's going to be a lot of construction. They have the chemicals as far as the sorbent materials. Land use, they'll have a pretty big footprint. Then they're going to have the materials and also the CO2 storage system. So those are contributors to the greenhouse gas emissions for direct air capture systems. Terrestrial carbon removal includes things like reforestation, afforestation. So these technologies would require a lot of land use, transportation, maintenance. You have to look at the natural cycles of the biomass decomposition, any sort of, road access and monitoring, the actual system. Those are contributors to the greenhouse gas emissions for terrestrial technologies. And then finally, mineralization, enhanced weathering. This is based on the concept that, CO2 can be absorbed in certain types of rocks. So they could be crushed or powdered, spread on fields to enhance plant growth. So components of terrestrial CDR that contribute to LCA greenhouse gas emissions include things like land use, transportation of the rocks, maintenance of the system. You have to look at the biomass decomposition, things like that. If there's any sort of rock mining, powder production, transportation to the fields. So those are the technologies we looked at. Again, these technologies are emerging. There's kind of a rapid development improvement in the processes. They involve, different processes, energy sources, embodied emissions, things like that. We think that, there's costs are a factor for deployment. Some of the technologies will require, construction of large facilities, operations 24/7 that have to be supported. I think you have to look at the, carbon removal potential. Can it make a big difference in the actual volumes of CO2 that are removed from the atmosphere? And then, we think these deployment factors are really important. So, for direct air capture, you need a low carbon energy source, and you might need access to geologic CO2 storage sites. And if those are together, that's your best scenario. BECCS requires obviously, access to a lot of biomass, transportation corridors. Terrestrial and mineralization might need access to, large areas of land. So our first step in our life cycle review was to look at literature values, and these values show a wide range of net CO2 removal rates. So here's our 5 technologies here in this chart. You can see what we found in the literature was that, for direct air capture, anywhere from 40 to 99% was listed as a net CO2 removal. For BECCS, it ranged from 0 to 90%. A lot of that was related to the ratio of biomass to fossil fuels in the plants. So a lot of the plants, again, are planning to burn a mix of fossil fuel with biomass. And then terrestrial and enhanced weathering, you can see the literature values range from 30 to 99% and 74 to 99%. So kind of a wide range in some of these life cycle analysis results. We think most of them did identify the big drivers for the greenhouse gas emissions. For direct air capture, the energy source was a big driver. They need a low carbon energy source to run their plants. For BECCS, it's the emissions from the fuel sources, upstream biomass processing. And for terrestrial mineralization, you have to look at land use, upstream processing, and permanence as use. So our next step was to run these 5 technologies through this streamlined energy and emissions life cycle model for a 1 million ton per year scenario. This graph on the bottom kind of shows the results of those. This is for the kind of light blue, so the base, like a 1 metric ton, and then up here in the purple shows the emissions generated, and this kind of dark blue shows the difference. So what we saw in our model was, for CDRs around the net carbon dioxide removed around 67% to 69%. For bioenergy, we did use a like a fuel mixing scenario based on what we saw out there, and that was 36% net CDR. Terrestrial net CDR was around 92%, and then for mineralization, it was about 87%. So yeah, so that kind of shows you what we saw in our model as far as what the big contributors to the greenhouse gas emissions were. This chart here on the right kind of shows you we tried to break things out by category as far as what are the emissions generated with these different systems. You can see for direct air capture, the actual capture plant operation, construction, and embodied emissions. That's a big driver for the emissions generated from direct air capture. So you need, a low carbon energy source to power these systems, and that's currently that might not be available. For bioenergy with carbon capture and storage, it's the upstream, the biomass, harvesting, also transportation and capture. And then for terrestrial mineralization, a lot of the greenhouse gas emissions are related to things like, land use and site preparation and transportation. And as far as geographic and market factors for deployment, obviously these are also factors for CDR technologies. Here in the lower left there of your screen is a map showing, green energy availability, and where darker green is where more green energy is available, and then these kind of black outlines are these major sedimentary basins where carbon storage would be available. So DAC technologies would need both of those features to be successful, we think. So where those two items coincide would be, areas where you would consider direct air capture deployment. And then also market factors are important. So there's a lot of upfront construction and long-term operational costs associated with some of these technologies, like direct air capture and BECCS. So building these plants could have a high initial cost, but then they would be able to recoup some of those costs through 45Q tax credits, and in the case of BECCS, they'd be able to sell the power they generate at their plant. So in summary, these CDR technologies are being scaled up from experiments and pilot scale tests to industrial scale. It's important. We think it's really important to consider these cradle to grave life cycle greenhouse gas emissions that might be associated with the technologies. You have to look at the upstream, gate to gate, downstream activities. Some life cycle assessments only address individual components of the CDR process. Our study suggested that CDR technologies would have effective cradle to grave net carbon removal rates of 65 to 95%. All these technologies would generate greenhouse gas emissions in some way. We think it's important to account for these with life cycle analysis, and then we think it's really important to test and monitor these technologies. It might take once they get to scale, it might take years for people to really understand how the operations balance out. You think there'll be obviously some initial construction shakedown periods after they're initially constructed, and they should be given some some leeway to optimize their operations, as we imagine that the operations will improve over time as they kind of find ways to reduce their greenhouse emissions, and things like more green energy becomes available to run some of these plants. So with that, that's all I have on our study. I'll be happy to answer any questions if there's any out there.
Great. Thank you so much, Joel. Really appreciate all the work that you and your team did on this study. It was a really great piece of work. there are some questions in the chat, so feel free to take a look at those. And I'm just going to remind everyone, there's a few people who have raised their hands. If you've raised your hand and you'd like, you have a question or like to make a comment, just please do so in the Q&A box. So just a reminder on that. Now, this first question, I'll give you a chance to answer it, and then Dave, I'll give you a chance after yours as well. This is from a reporter with S&P Global. Given the recent Microsoft and Amazon direct air capture purchases, how long will this voluntary market demand last for quote unquote high quality CDR credits before CDR companies will need a compliance market to make money? I don't know if you have an opinion on that or not, Joel.
Yeah, that was not a focus of our study. We were more focused on the life cycle analysis, but I think you do need to look at the timelines and the technology readiness levels of these technologies. Again, I imagine it's going to be, before they get to scale of like millions of tons per year, it's going to take a while to construct these plants and get these projects underway. It could be, in the order of 5 to 10 years. So that's the kind of timescale I would imagine.
Right. Thanks. And Dave, I see that you've unmuted yourself. If you want to go ahead, take a step.
So I wouldn't try to pull out my crystal ball and predict how long demand for those sorts of things will last, but I just, from the view of an observer, I think that those companies are responding to consumer desire to do business with organizations that prioritize these sorts of climate concerns. And so I don't see that going away. I think the voluntary markets can persist for a long time, potentially even beyond beyond regulation being implemented. But again, that's not my area either. It's just the view of an interested person.
Appreciate that, Dave. Thank you. And Joel, another question for you. What guidelines did you use for your LCA? For example, did you use GCI's assess CCS for the techno-economic analysis and LCA, or another source?
We mainly use some of the guidance from the U.S. Department of Energy and NETL. In their career, they have a nice guidance website and a bunch of good reference material. So we mainly use that. In addition, we used, we've done a lot of work on CO2 storage and CO2 capture. So we use some of our own experience, like running field projects, as kind of a reality check on our results. But again, I think our big message is like, you need the real world testing, the real world operational data to really understand how these things, work, rather than, some of these, it's kind of hard to get a feel how it's going to work from a unit process versus like, out in the field, actually running the systems, on a continuous basis.
Got it. Thank you. And then kind of a similar question from the earlier one. Any thoughts about the quality of these technology for carbon credit sales? So much going on with carbon markets right now. Nature-based are getting pounded. So maybe kind of an MRV component in that question as well. If you want to touch on that.
Yeah, I mean, that's a great question. And I think it's everybody has to kind of be playing by the same rules and look at the whole life cycle. Again, I think, the biggest value is from the real world operational data. So we think you have to monitor this stuff and test it and get some actual operational data. So we were working on one CO2 storage project, and we actually got the electric bills and the gas bills from their capture facility. And that's the level of like real world data we think you need, rather than, some sort of unit process where you say, well, I kind of like did this in ChemCAD. This is what I think it's going to look like. It's like, the proof is in the pudding. Like, when you actually look at their bills and see, like, these guys are, spending, they're spending like tens of thousands of dollars a month on their gas bills versus, you compare it to your gas bill, you get an idea of the scale of these projects.
Got it. Thank you. And then we have a comment from Ryan Baker on the LCA guidelines. NETL participates in the GCI, so the TEA and LCA guidelines will be very similar. So thank you, Ryan, for providing that extra context. Another question in regards to slide 14 of your presentation. Are emissions reported for CO2 capture part of DAC for the capture step only, or capture and regeneration steps? If the latter, what was the rough breakdown between these two steps?
It was the full cradle to grave for both capture and regeneration. And the CO2 compression, transport, storage. So we tried our best to do the full cradle to grave type approach. I don't offhand know the breakdown between capture and regeneration. I'd have to look at some of our, I think it might be in our report. I think our report is posted on the USEA site, but offhand, I kind of don't have that level of detail.
Got it. And I will, I'll post that link here in a moment. One last question regarding reforestation and afforestation. Did you all kind of look at the potential for wildfires kind of undermining the CDR benefits of those methods?
So not specifically, no. We didn't specifically look at that.
Got it. Yeah, I was just curious. I'm as my background shows, based up in the Seattle area, so we get a decent amount of wildfires in the West. So I feel like I remember last year Elon Musk had made a Twitter post about potentially funding the best CDR technology, and there were a lot of pithy answers of, oh, just grow more trees, and so I think that's a I guess externality that people don't really think about as much. So was just kind of curious about that.
Those are like the natural cycles that we mentioned. You have to look at the biomass, the ultimate fate of the biomass. Is it just going to decompose, or are there going to be forest fires? So yeah, you have to consider all that, and it's really difficult to monitor that, because it could take decades, right, to really understand things, how it all shakes out. So yeah, that's a kind of difficult thing to analyze.
Fair enough. All right. Well, thank you so much, Joel. Again, really appreciate the great work that you've done. Appreciate you taking the time out of your day to join us. With that, we're gonna move on to Dave Luebke to discuss NETL's Direct Air Capture Center, and the great work that you all are doing there or planning to do. I'm excited to kind of hear the progress. I know this is kind of a relatively new program. So Dave, you should be able to share your screen. I see it starting.
Can you all see that?
Yeah, if you want to switch the display settings, we see your kind of notes, the notes page, if you know what I mean.
Yeah, I just need to figure out how to do that.
Right to the left, there's that display settings button. There we go. Yep.
Okay, excellent.
Perfect.
Thanks for bearing with me for a second, folks, and thanks for the introduction, Alex. So I am Dave Luebke from National Energy Technology Laboratory, and I'm going to talk to you today about the NETL Direct Air Capture Center. And sort of our mission, our what we're trying to do, and the progress that we've made in that area. So there has been an explosion in interest in direct air capture over the past few years. If you look back a decade, and these are the publications in the Science Direct database, you see that we've gone from just a few each year to hundreds. And that's really indicative of an understanding, both in the folks funding the research and the people doing it, that this is a critical piece of our carbon management strategy and something that we need to push because these techniques are relatively undeveloped. Jason talked about the startups that are working in these areas. So he was looking at from the business side, how those were pushing up through the early stage funding, and maybe some of them starting to see some Series A's and some later funding round events. And that talks about how the businesses are progressing. You think about how the technologies are progressing, that's a whole different kind of a question. And this is just a conceptual view of the technologies that are out there for direct air capture. For anybody who's not familiar with technology readiness level scale, 1 is a technology that you just sketched in your lab notebook this morning, so it's just an idea. And 9 means that that technology is available for adoption around the world. So what you see in direct air capture technologies is a clustering in sort of the 2 to 4 or 5 kind of a range, with only a few moving up toward that level of commercialization. So given that we see a need to implement a lot of carbon dioxide removal in general and direct air capture in particular by 2050 to meet our climate goals, what do you do about that? Well, if you're the National Energy Technology Laboratory, which is an organization with a couple of decades of developing point source carbon capture and a big set of facilities and a large group of professionals with strong competencies in development and acceleration toward commercialization of very similar technologies, you say, hey, well, we have all this capability, let's use it to help the technology developers that are out there. So the way that we're doing that, one of the ways that we're doing that, is the Direct Air Capture Center, which is a test bed facility, which will be located here in Pittsburgh, Pennsylvania, which will be available to work with all these technology developers to test the performance of their DAC technologies. We're going to provide, a standard or specialized testing depending on the needs of the test partner. We'll have access available to all kinds of organizations, and you get to collaborate if you would like with our professionals here to advance your technology and maybe develop new versions of it. So we didn't delve into my bio, but my last gig before this was in startups. And so when I became technical director of the DAC Center, one of the first things I did was fall back on that experience. And the thing they tell you over and over again in startups is don't sit in your office trying to sort out what the needs of your customers are. Go out and talk to them. So that's what we did. We went out and we talked to all kinds of DAC developers, and we asked them questions like, what can you do? What can't you do? What are the things that are hard? What would you be willing to pay money to have somebody help you with? And so over the course of many, many conversations, several different areas of need started to emerge. So at the lab scale, so these are materials, we started to hear, okay, well, it's pretty easy to take an isotherm on a material, find out how much CO2 it absorbs, what will cause it to desorb that. Pretty easy to even do that in the presence of other gases, so you can understand selectivity and these kinds of issues. But when you start to incorporate humidity, when you start to think about things like steam regeneration, and most critically, when you start to run these things for thousands and thousands of cycles so that you can really understand whether or not they're stable enough to be practical out in the real world, that gets hard. And the things that are involved in doing that become more expensive, and the time to spin those capabilities up goes way up. So those are that's one set of needs. The next step in sort of scale up and commercialization of this technology is, okay, I've taken this material, now I'm going to fabricate it into a form factor. And that form factor could be a monolith. It could be some particular kind of a contactor. But the idea is this is something that you can take and multiply it and scale up to get the kinds of fluid flow and pressure drops that you're looking for. So now you've got all the same problems you had at material scale, but you've also at this, we'll call it module scale, got the need to observe the fluid dynamics of your system. And also this is at a larger gas flow, which is a little bit more difficult to work with. So finally, the last thing that we heard is that the great thing about working in direct air capture is that you can set your prototype up in the back parking lot and test it. You don't need a power plant attached to it. You don't need, like you would with point source. You don't need specialized conditions, none of that. The downside of it is that you're at the mercy of the atmospheric conditions. So the technology is functioning in one particular state of temperature and relative humidity. And temperature and relative humidity changes diurnally, it changes seasonally, and it changes geographically. So the system that I set up in Pittsburgh and test in my backyard in September will function much, much differently than the one that's set up in Arizona in August. So it's very difficult to, without much testing, understand the full performance of any given prototype. So what we're doing at that scale is we're going to provide environmental chambers, which will let you set up your prototype in them and will give you exactly the climate conditions you're looking for. And that can serve as your last kind of lab test before you begin to deploy into the field. So I'm going to delve pretty deeply into the technical side at this point. So bear with me. So at the material scale, we're really talking about a breakthrough experiment. So what you're doing is metering air into a chamber that is containing your material. You're controlling the CO2 concentration, the relative humidity, the temperature, the pressure, passing it over and watching the absorption. It's called a breakthrough experiment, and I'll show you why in a minute. But you observe all the same quantities coming out until the material is saturated. Then you change the condition to your regeneration state, and you watch the CO2 evolve. So if you do this for 1,000 cycles or so, you now have a good understanding of how your materials perform for a particular set of DAC conditions. We designed such a system. I showed you the conceptual sketch. This is the 3D rendering of it, which resulted from the detailed engineering design. One of the things NETL brings to the table that I know from personal experience in startups that many technology developers don't have is a strongly knowledgeable and capable set of design engineers that can work with us to build these sort of experimental systems. And also, on the other side of this, excellent fabrication technicians, which can take these designs and turn them quickly into systems that are real and in the laboratory and can be used. So what I'm showing you here is a picture of our material scale prototype system set up in our facility in Pittsburgh. That is the first system to come online, and we have shaken it down. It's operational. We're working on benchmarking it with multiple materials now so that we have a very solid foundation on which to begin testing. So these are the detailed specifications associated with that system. We have the capability of varying CO2 concentration from 100 to about 600. Of course, 420 is about the range one expects in the atmosphere. Ability to change airflow rate from 10 to 500 liters per minute, which equates in the 2-inch diameter reactor tube to nominal velocities in the range of 0.1 to 4 meters per second, which is a good broad range for these kinds of tests. We can control the air from 5 to 95% relative humidity, and we have a temperature range available for regeneration or capture in the lower part from room temperature up to 150 C. Regeneration, we provide a vacuum down to an absolute pressure of about 2 pounds, and we have roughly saturated at room temperature or at ambient pressure steam, which can also be used for regeneration. So a big variety of capability there for looking at different kinds of materials. At the bench scale, we are talking about much the same kinds of experiments. They're still breakthrough situations, but we're adding some additional capability. We're able to now take, say, 1 foot by 1 foot by 1 foot modules that contain these form factors that are the first step toward scaling up, and take a look at them in terms of performance. And so we've got all the same capability in terms of what the breakthrough experiments can do, but now we're adding in some capability to do things like regeneration with joule heating of the monolith, for example. Here again, we have the 3D rendering that resulted from the detailed engineering design of a prototype system at that scale. And this is the system sitting at the fabricator. It's currently being installed in our laboratory here in Pittsburgh. We expect the shakedown to start happening early in October and to have that system online for benchmarking early next year. We will then take these 2 prototypes and replicate them so that we get, by the end of this process, to about 10 of the lab scale, material scale systems, and perhaps 5 of these larger bench scale systems, which should give us the amount of capacity we think we need to work with a number of testing partners who are interested in collaborating with us. Finally, we have the small pilot scale facilities. These are the prototypes that I talked about. We'll have 2 test bays for these systems. These prototypes can be pretty large, up to the size of a 20-foot shipping container. So you're talking about 8 feet or so wide, 8.5 feet tall, 20 feet long. We'll have available control rooms out in that facility for monitoring and collecting data on the prototypes. We'll have all the necessary utilities, and we will be able in those rooms to supply air in the range of 10 to about 110 Fahrenheit with the full range of relative humidities. So as a test bed facility, we have a few different types of agreements available for working with folks. The simplest is a contributed funds agreement, where we write a scope of work. We don't really expect any IP to be generated, and we go off and do that work here and get you the data that you need to progress forward. We also have, if you're interested in leveraging all of this great competence and capability that we've got here at NETL in terms of development, to advance your technology, to work out new, perhaps versions of it, we can do a CRADA, which is a collaborative agreement where we determine what the IP terms look like at the beginning and then do the work together. And both of those are available for our partners. So just to really dig deeply into this, if you're actually interested in working with the particular contaminants that may evolve from any of these systems, because there have been some concerns in certain places that, hey, we're taking the CO2 out of the air, but what are we putting in? We'll have a capability of looking at that for your technologies. If you're talking about these processes, there's really a few places where you might see evolution of trace contaminants. So you might lose them into CO2 or into the air in the gas phase, or many of these produce condensates. And so there might be losses of pollutant materials in there as well. So we'll have the capability of looking at the gases, looking at the condensates, and also tracking the loss of material in the reactor. So how might we do that? Well, so really across the board, the simplest way of looking at losses of active material in the capture material is elemental analysis. Most of these are based on, not all of them, but most of these are based on nitrogen compounds. So tracking nitrogen loss is one effective way of watching the sorbent or solvent material move. In the liquid state, we'll have access to GCMS, which will let us look at trace compounds there. And in the gas phase, we'll have access to PTR time of flight mass spec for looking at trace compounds down to the low part per billion level. We are, as I said, our first test system is online now. We expect to bring additional capacity online throughout this year and next until the entire capabilities of the facility are online in early 2025. This is my contact information. I encourage you to get in touch with me if you're interested in working with us. And as always, the United States government disavows any knowledge of my actions.
Thank you for that, Dave. That was great, and really appreciate hearing everything that you're doing at the DAC Center. I think due to schedules, I had originally wanted to kind of have you go first to discuss the DAC Center, and then discuss how that can flow into the AirMiners work, and then have Joel discuss kind of the LCA aspects of it. So we kind of did it a little bit backwards, but appreciate you taking the time to do that. As mentioned earlier, if you have any questions or comments, please feel free to enter them into the Q&A box or the chat. One question that I have for you, Dave, you had that kind of conceptual slide on the different TRL levels, and it was, it showed the sorbents versus the solvents, and it looked like there's a lot more sorbent technologies. For those of us who aren't as technical, is there a reason for that?
So I wouldn't say there's a reason for that. There are advantages to both the solvent and the sorbent systems. There are, I think, a wider variety of potentially effective approaches to the solvent side of this, or to the sorbent side of this. So I think that's a big part of it. The solvents tend to be more or less reactive to the environment that they're capturing from, while the sorbent materials tend to capture at more or be more impacted by the conditions, but they can be regenerated often at lower temperature, which makes it a slightly less strenuous process from that point of view.
Got it. Okay. Well, thank you for that. Not seeing any other questions, comments coming in. I guess that's kind of the downside of being at the end of an hour plus. Here we go. What types of entities do you think will be primary users of DAC technologies? Hard to abate sectors, power companies, private developers selling offset credits, etc., and why?
So I think we're seeing really the emergence of a market here. And it isn't entirely clear the degree of integration that will occur. So it's quite possible that all kinds of entities could implement direct air capture. But in order to do so, you need to capture the carbon dioxide, you need to transport it, you need to store it, and ultimately you need to account for it and sell the resulting credits or make use of them. So likely, we're going to see a whole lot of different approaches to that, with companies taking different slices of that pie throughout. In most areas, you eventually see a lot of specialization, but I think we're years from knowing if that'll really be the case in carbon markets.
Got it. Thank you. And then all of a sudden we have a lot of questions rolling in. Can you name any of the liquid and solid sorbent technologies in TRL 7 through 9?
Well, I could, but I think a web search of DAC technologies will get you the major companies that are associated with those things pretty easily.
Got it. And then where do you think we are in terms of invention level in TRL relative to what we can scale by 2030 or 2050? Have we invented what we need to at this point, or is there still a lot of work to be done there?
So I think the short answer is no, we haven't invented what we need to invent at this point. I can tell you that I got into point source capture in 2002. And in 2002, the state of point source capture was much like the state of direct air capture today. So there were a large number of technologies at kind of the lower tiers of the TRL, with only a few that were commercial at some scale or approaching commercial at some scale. And so over the last 20 years, we've seen that evolve, and we've seen multiple technologies now that are really ready for implementation at full scale for point source capture. So I think the worst case scenario is that it takes us 20 years to do that again. But I'd like to think, and the reason I'm doing the job that I'm doing is that we have all this experience from point source. We can learn from that so it doesn't take us that long. So I am quite optimistic that while we haven't invented everything we need to invent yet, we have time and the resources that we need to do so.
Got it. And on that note, things like AI, for example, do you see those helping kind of accelerate some of this work or other advances in computing?
So I'm a very nuts and bolts engineer. I am build it, go to the laboratory and test it kind of a guy. But I think the advances in machine learning in particular, and some of the AI as well, based on what I've seen and what I'm hearing from my colleagues that really understand those things, are going to accelerate this. I think there's the ability to analyze patterns in data, to model molecular scale interactions and process interactions in ever more sophisticated ways, will allow us to really move forward some of these things more quickly.
Thank you. And then for those who are interested in working with the DAC Center, is participation government funded, or do folks pay for space at the lab? And then how do they qualify?
So we work on a cost of framing kind of basis. So there's the ability just to bring in funding, pay for our operating expenses and work with us that way. There are also programs emerging that would allow people to propose doing testing at these kinds of facilities and hopefully get some funding to work with us that way.
Got it. And then it seems that your lab and bench scale units are more suitable for adsorption testing. Is this correct? And then how about the pilot unit? Could you please inform us when your pilot unit will be on stream?
Absolutely. So the two systems that I showed for the materials and module scale are definitely primarily designed for adsorption. The reason for that is that while we really want to work on absorption, so solvents, it's tough to figure out how you design a general use test system at those scales, which a variety of different technologies and solvents could use. If you have ideas about that, I strongly encourage you to get in touch with me and let's talk about it. And we'll see if we can't make that part of this suite of systems at the lab and bench scale that we'll be building after the implementation of these prototypes. As far as at the pilot scale, which will be available in early 2025, we will be able to accommodate liquid solvent systems as well. Those prototypes can really be whatever they need to be, as long as they fit into the space that we have, which should accommodate more or less any technology at that scale.
Great, thank you. Some things to look forward there. Do you mind if I share your email in the chat?
No, please do.
So there's that. It looks like there aren't any more questions or comments at the moment. So there are a couple other things that I wanted to mention. As Joel said, the report that he discussed is on the USEA webpage. So I've included that in the chat there. And then we also have a couple of announcements for kind of upcoming activities that I just want to make sure and share with everyone. Are you able to see my screen here?
We are.
All right. So one is this upcoming webinar that we have looking at FECM and CETP funding opportunities with CCUS, hydrogen, and renewable fuels. That will be on October 16th at 10 a.m. Eastern. And then also wanted to make everyone aware of this interesting toolkit from our partners at the United Nations Economic Commission for Europe, UNECE. They've developed a carbon neutrality toolkit to support policymakers in making informed decisions towards the implementation of the 2030 Agenda for Sustainable Development and the Paris Agreement. A lot of great resources on this page. So certainly encourage you to take a look. You can see the URL at the top there. With that, I'm going to do one last check here. Not seeing any more questions or comments. So with that, I just want to say, Dave, Joel, thank you guys so much. Jason as well. He left, but just want to say thank you guys so much for taking the time out of your days to join us here. I was really excited to host this webinar. I think CDR is a really exciting space. I don't think we reach our climate goals without it. Yeah, happy to see all the great work that's going on, and excited to see what's going on in the future. Had a lot of questions and comments come in, so I think that shows the interest level of folks out there. So thank you again. I hope everyone has a great rest of your week, a great weekend. I have a request here to share my email address, so I'll just do that real quick. And yeah, we will see you next time, hopefully at our next webinar on the 16th. All right, thank you everyone, and have a great rest of your day.